In this chapter, we are going to be looking at expressions and equations that contain the exponential form. It is not something that you guys are unfamiliar with, because for an exponential form, it simply looks something that is like this, where x here is called the exponent or the index, and a here is called the base. There are other exponential forms that we are going to be seeing in our syllabus. Let me introduce to you three more. So one of them is this, 1 over a to the power of m. An example, 1 over 2 to the power of 3. According to what we are seeing here, this can also be written as 2 to the power of minus 3. Our calculator, in fact, read in the same way as how we are interpreting this. Let me show you. So, for example, if I were to press the left-hand side into the calculator. So, on our calculator, I'm going to press 1 over 2 to the power of 3. We know 2 to the power of 3 is 8. So this is going to be giving us a 1 over 8. And let's see whether this is going to be true if I were to press it as 2 to the power of minus 3. So let's try 2 to the power of minus 3. This is equal to 1 over 8. So yeah, they are the same. Let me give you a few more examples. Let's say I have 1 over 5 to the power of minus 4. This is the same as 5 to the power of minus 4. This is 5 to the power of 4. Let's do a quick numerical verification. So if I were to press it in as 1 over 5 to the power of minus 4, let's see what we're going to be getting. 625. Okay, 625, is this the same as 5 to the power of 4? This is equal to 625, which means that if I have something that is like 7 to the power of, let's say, minus 6, this is going to be the same as 1 over 7 to the power of 6. This is one of the forms. Let me show you another one. The other one is going to be something that is like this, a to the power of 1 over m, or the index is 1 over m. So let's say we have a 2 to the power of 1 over 3. According to what we are looking at here, this can also be expressed as the cube root of 2. Let's verify this. So on our calculator, let's try to press the one that we are more familiar with first, okay, which is this cube root of 2. So it is going to be here, cube root of 2. This is 1.2599 and so on. So is this the same as 2 to the power of 1 over 3? Let's find out. 2 to the power of 1 over 3. This is the same, 1.2599 and so on. So if, let me give you another example. Let's say if I have a 5 to the power of 1 over 7. This can also be written as the 7th root of 5. Of course, we can press this into the calculator, but now I know I have another option, which is this. So, I mean, previously, maybe we will be just pressing this into the calculator. Here, it will be 7, okay? The 7th root of 5. So, 7th root of 5. This is equal to 1.25849 and so on. So is this the same as 5 to the power of 1 over 7? Let's find out. So 5 to the power of 1 over 7. This is equal to 1.25849 and so on. Okay, they are numerically the same. Let me show you one more, and this actually looks very similar to what we have here. A to the power of m over n. For example, 4 to the power of 3 over 2. According to what we are looking at here, this can be written as the square root of 4 to the power of 3. But of course, we can also write this as just simply square root of 4 to the power of 3. There's another version of this, which is going to be, according to what we see there, it is going to be the square root of 4 to the power of 3, which we also know that we can also write this as just simply square root of 4 to the power of 3. Let's use our calculator to verify this one more time. So 4 to the power of 3 over 2, let's press this into the calculator. So 4 to the power of 3 over 2. So 3 over 2, this is equal to 8. Let's check against this, or maybe I'll just press this into the calculator. So let me try this, square root of 4, close bracket, to the power of 3. Okay, we are going to be expecting ourselves to be getting 8. So this is equal to, 8. Okay, let's try this, square root of 4 to the power of 3. Let's see whether it is also going to be equal to 8. So square root of 4 to the power of 3. Let's try, this is it again. So these are the few other forms, other exponential forms that we will be very commonly seeing in our exams and in our homework and in our daily practice. So please remember them. They are going to be very useful for us to be interpreting and manipulating equations and expressions that contain the exponential forms. But these are not enough. I'm going to introduce to you some laws and some results that I think is going to enhance our ability to manipulate and solve equations that involve exponential forms even more. So I'm going to introduce to you these few laws here. They are the exponents law or the indices law. If a and b are numbers that are bigger than 0, and m and n, they are rational numbers, numbers that cannot be expressed as one integer over another integer. These are called rational numbers. So pi is not a rational number. So we are not going to be dealing with, in this indices law, right, we are not going to be dealing with something that is like 2 to the power of pi. Okay, so we're going to be dealing with something that is more of like 2 to the power of 7, where the base is positive and the index is a rational number. So the first law is a to the power of m times a to the power of n. This is a to the power of m plus n. We can actually deal with this without going through the indices law. But with the indices law, it makes the manipulations or the evaluation quicker and faster. So we definitely want to make use of them. But let me deduce for you why this is so. We have a to the power of m and a to the power of n. Why is this the same as a to the power of m plus n? Let me give a numerical example by replacing m here by a rational number. So let's say 3, and this I'm going to replace it by 2. So what is a to the power of 3? A to the power of 3 is just simply a times a times a. And a to the power of 2 is a times a. So a to the power of 3, a to the power of 2 is now going to be a times a times a times a times a to the power of 5. Okay, this is actually okay, right? Because we are just simply applying multiplication. But this is going to be that little bit slower if we were to be applying the indices law. Because this, if I were to apply the indices law, this is going to be just simply a to the power of 3 plus 2. It is a to the power of 5. So I can see it from here also. It is going to be multiplied by itself 5 times. That is why it's going to become a to the power of 5. We can also use the same way to deduce this second law, a to the power of m. I'm going to let m be equal to, let's say, 5, divided by a to the power of n. Let's say n is equal to 3. This, let's see whether it is the same as a to the power of 5 minus 3, which is a to the power of 2. So if I were to use multiplication and division, this numerator here is a times a times a times a times a, 5 of them, divided by a times a times a. So we know that this can be cancelled, which will leave me with a to the power of 2, which is 5 minus 2. Because we actually have 5 a's, 3 a's, so 5, 3. 3 of them will be cancelled in the numerator and the denominator. We're going to be just left with a 5 minus 3, numbers of a being multiplied to each other. So we have a to the power of 2. How about this? A to the power of m times b to the power of m. Is it really equal to ab to the power of m? And of course, it is going to be equal to, we are still going to try to deduce this, okay? We are going to memorize this, but let's deduce it. So let's say we have a to the power of 3, b to the power of 3. So if I were to re-express this into the multiplication form, this is going to be a times a times a, 3 of them, multiplied by b times b times b, which I can also re-express it as a times b multiplied by another a times b, and I have a last pair which is also a times b, which is a b, this times this times this to the power of 3, which justify for me this form. A to the power of m times b to the power of m is ab to the power of m. We are going to use the same strategy to verify this. So if we have a to the power of 3 divided by b to the power of 3, this will be a times a divided by b times b, which I can also re-express this as a over b multiply by a over b and multiply by another a over b, which is equal to a over b to the power of 3. One last one, which is this, a to the power of m, and the whole thing to the power of n is equal to a to the power of simply m times n. So for example, if we have a to the power of 3, then the whole thing to the power of 2. This is like a to the power of 3 times a to the power of 3. And if I were to then make use of what we have already deduced, a to the power of m times a to the power of n, this can be a to the power of 3 plus 3. This is a to the power of 6, which is actually going to be a to the power of 3 times 2, according to the last law that we are looking at here. Let me give you two more results. These are not exactly the laws, but they are results that are going to be definitely useful in terms of us solving for questions later. A to the power of 0 is always going to be equal to 1. Let me just show you on the calculator. Can you pick a number for me? Or rather, you just press any number into your calculator. Let's say 5. 5 to the power of 0. Let's see what we are going to be expecting this to be. It is 1. A to the power of 0 is 1. Let's go for a strange number. Let's say 218. 218 to the power of 0. It is still going to be equal to 1. A to the power of 0. Regardless of what is the value of a, it is always going to be equal to 1. And if I'm able to form an equation such that an exponential form with the same base are equal to each other, a to the power of x is equal to a to the power of y, then we can say that x is equal to y, but provided that a cannot be equal to 1. Because if a happen to be equal to 1, then 1 to the power of anything is just going to be equal to 1. So it will definitely be 1 is equal to 1, but it will not imply that x is going to be equal to y. Okay, so this is the restriction. And I guess now we are ready. We can try to make use of the things that we've discussed and see whether we can apply that to manipulating expressions that has the exponential forms and equations that contain the exponential forms. Let's take a look at some questions. So we're going to be referring back to this now and then. And let's take a look at our first question here. Let's try to simplify this. So we are looking at 8 to the power of minus 2 over 3 multiplied by 3 to the power of minus 2. Let's try to simplify this and let's see whether we are going to be able to get a 1 over 36. So let me flesh out this again because we are going to be using these few expressions and these few laws. So this, okay, 8, I'm going to re-express it. This 8 here, I'm going to re-express it as 2 to the power of 3. Then to the power of minus 2 over 3 times this, I'm going to write it as 1 over 3 to the power of 2. I'm already applying this, okay, 1 over a to the power of m. So I'm applying that here. And for this, I can actually apply this law here. A to the power of m to the power of n is a to the power of m times n. So this is going to be 2 to the power of 3 multiplied by minus 2 over 3. So this is going to be multiplied to 1 over 3 to the power of 2, which is 9. And this times this will be 2 to the power of minus 2 times 1 over 9. And if I were to apply this form of exponential forms here, it is going to be 1 over 2 to the power of 2 times 1 over 9. This is going to be 1 over 4 times 1 over 9. And now we got it, 1 over 36. Let's look at another one. Let's take a look at this. This, we have a 81 to the power of 3 over 8 times the square root of 32 divided by 18 to the power of minus 1. Okay, we're going to try to make use of what we have just talked about again. Let's see how we can manipulate and simplify this. So 81, we can simplify this or we can re-express this into an exponential form. 81 is like 3 to the power of 4. So we have this to the power of 3 over 8. And 32, we can also re-express it into an exponential form, which is 2 to the power of 5. And this is square root, so I'm going to power this to 1 over 2. And then 1 over 18 to the power of minus 1, we're going to rewrite it as 18 to the power of minus 1. So we have this, and now this is going to be 3 to the power of 4 times 3 over 8, which will give me a 3 over 2. Then times this is like 2 to the power of 5 over 2 times 18. This is 18 to the power of 1. And 18, I can rewrite it as 3 to the power of 2 times 2. 18 is like 9 times 2. And the reason why I am doing this is because now I have the same base, which I can then combine together to become 3 to the power of 3 over 2 plus 2. And these two bases here, I can also combine them together, since they are the same, into 2 to the power of 5 over 2 plus this. This has an index of 1, so 5 over 2 plus 1. And this will be 3 over, this is equal to 7 over 2. And 2 over, this is also 7 over 2. And now we can apply this one here, because I have a to the power of m times b to the power of m scenario. So this is going to become a 3 times 2 to the power of 7 over 2. So we have this as a 6 to the power of 7 over 2. So these are what we are doing by making use of what we have just talked about to manipulate an expression that contains the exponential form. Let's take a look at equation solving, equations that contain the exponential form. So let's take a look at this question here. We are going to try solve this. And now here we have a 2x to the power of minus 3 over 4, and this is equal to 27 over 4. Let's try to make x a subject in order for us to solve this equation. So I'm going to remove this 2, so we have a x to the power of minus 3 over 4. This is equal to 27 over 8. And in order for me to make x a subject, I'm going to make use of this law that we have discussed, which is this. Okay, a to the power of m, the whole thing to the power of n is a to the power of m times n. So I'm going to raise this left-hand side here to the power of minus 4 over 3. I'm going to do the same thing to the right-hand side, 27 over 8 here. It is going to be raised to the power of minus 4 over 3. And the reason why I'm doing so is because if I were to apply the law of indices to this, then it will be this multiplied by this for the new power or the new index of x. And what is this multiplied by this? It gives me 1. So here we have a x to the power of this times this, which is 1. It's going to be equal to 27 over 8. Let me just write it down. 27 over 8 to the power of minus 4 over 3. And now I've made x a subject. Let's try to simplify this. So x is going to be equal to 27 over 8. We can actually re-express this into the exponential form, because 27 is like 3 to the power of 3 and 8 is like 2 to the power of 3. So we have this to the power of minus 4 over 3. And this will be the same as, if I were to use the indices law, 3 power 3 and power 3. This is the same as 3 over 2 to the power of 3. And this is going to be to the power of minus 4 over 3, which will then give us this multiplied by this for the new index. So this to the power of 3 times minus 4 over 3 gives me a minus 4. And to manipulate this further, I'm going to bring the minus 1 in. This is what I mean. So it will be 3 over 2 to the power of minus 1 to the power of 4. I'm actually reversing the effect of this. So I'm actually going from the right-hand side of this to the left-hand side. So I brought the negative 1 in, which will then leave me with this. And now if I were to apply this that we have talked about, then this will become 1 over 3 over 2. And this is going to be to the power of 4, which means that we have a 2 over 3 to the power of 4. And this will lead us to 2 to the power of 4, which is 16, divided by 3 to the power of 4, which is equal to 81. So x is equal to 16 over 81. Let's try solve another equation. Let's try solve this. So what we have now is 10 to the power of x plus 1. This is equal to 25 to the power of x minus 1 times 4 to the power of x. Let's try to solve for x. So for this here, I'm going to rewrite it as 10 to the power of x multiplied by 10 to the power of 1. We are using the indices law that we have discussed. So I'm using specifically this. And as for this, I'm going to rewrite it as 5 squared into its exponential form. Then this to the power of x minus 1 times 4. I'm going to rewrite it as 2 squared. Then this to the power of x. So now we have 10 to the power of x multiplied by 10. This is going to be 2 to the power of, 5 to the power of 2 times this. So it is going to be 5 to the power of 2x minus 2 times this is going to be 2 to the power of 2x. And I'm going to re-express this further as 5 to the power of 2x, 5 to the power of minus 2 times 2 to the power of 2x. So we have here this 10 is equal to this and this. We can actually combine them together because they share the same power. So I can make use of this to rewrite it as 5 times 2. And this is going to be to the power of 2x. As for 5 to the power of minus 2, we can actually rewrite it as 1 over 5 squared. So now we have 10 to the power of x times 10. This is going to be 10 to the power of 2x. And here we have 1 over 25. I'm going to multiply 25 across to the other side. So 25 times 10, this gives me 250. And this 10 to the power of x, I'm going to divide it across to the other side here. We have 10 to the power of 2x divided by 10 to the power of x. And now for this, since they share the same base, I can rewrite this as 10 to the power of 2x minus x. This is equal to 250. So 10 to the power of x, now this is equal to 250. And in order for me to solve for x, I'm going to make use of what we have discussed in the chapter on logarithms. So if you are not well versed with logarithms, please make sure to check out that chapter first because we need the idea in order for us to proceed from here. So from here, applying logarithms, I'm going to try to common log on both left and right hand side. So I'm going to log to the base 10 on the left and log to the base 10 on the right. So on the left, this will become LG 10 to the power of x. This is going to be LG 250x. I can bring it forward. So we have x log 10. What is log 10? Log 10 is 1. So here is going to be 1. This is equal to log to the base 10 of 250, which means that x is going to be this, which I can just press this into the calculator. So from the calculator, log of 250. This is equal to 2.40 to 3 significant figures. Let's move on to another equation. For this other equation here, we have this e to the power of 2x plus 32 is equal to 12e to the power of x. And this e here is actually a constant. Okay, we're going to be seeing this e as a constant in a lot of other questions in our O-level math and the math that we're going to be dealing with next time, because this e, just like pi, it has already been predefined. This e, let me just show you. This e is the number 2.718281 and so on. It is an irrational number. It is called the Euler's number. In fact, we have e in our calculator, and this e is here. E, if I were to let it to the power of 1, we will be able to see its number. It is 2.71828 and so on. Okay, I mean, you can see more numbers here than the one that I've typed out here. So please take note. Okay, we are going to be just taking it as a constant for now, but we will be seeing this quite a lot of times from in our math from now onwards. Okay, so let's take a look at this other question. Here, question number 4. So in this question number 4, we have e to the power of 3x plus 32. This is equal to 12e to the power of x, where e is the Euler's number, 2.718 and so on. it is a constant. And we are supposed to solve for this. Oops, I've copied this wrongly. So this is supposed to be equal to 2. So e to the power of 2x, this is in the exponential form. E to the power of x, this is also in the exponential form. We are supposed to solve for e. And I'm going to try to bring everything over to the left-hand side, which will give me e to the power of 2x minus 12 e to the power of x plus 32. This is equal to 0. I'm going to try to re-express this as e to the power of x squared using the indices law that we have discussed, minus 12, and this is also e to the power of x plus 32. This is equal to 0. So in this equation, we actually have a common expression. It is in its exponential form. It is e to the power of x. So what I'm going to do next is I'm going to try to let y be this e to the power of x. Because the moment when I do so, this equation will become y squared minus 12y plus 32 is equal to 0. And now we have a quadratic equation. And to solve for this quadratic equation in terms of y, we're going to factorize it. Factorizing it gives me a y minus 4 multiplied by y minus 8 is equal to 0. This tells me that y is equal to 4 or y is equal to 8. But let's not forget what y represents. Y represents e to the power of x. So this is 4, and e to the power of x, this is 8. And in order for me to further solve for x, I'm going to once again make use of logarithms. I'm going to natural log on both sides of the equation, ln. So here, I'm going to do a ln of e to the power of x is equal to ln of 4, which means that if I were to bring x forward, I will be left with a ln e, and ln e is 1. So this is equal to ln 4, and I'm going to do the same thing for this. So ln e to the power of x is ln 8. X, I can bring it forward, it will be multiplied to ln e, and ln e is 1. So ln x is going to be equal to ln 8. Let's look at another similar question, question number 5. So here, we have a question number 5 already displayed. So in this question number 5, we have a 3 to the power of 2x plus 1 minus 3 to the power of x plus 2 plus 6. This is equal to 0. So let's try to solve for this. This is actually very similar to question number 4. So I'm going to use the experience that I have in question number 4, which is to actually get an equation that contains just one single exponential form. And then letting it be equal to y, letting it be equal to some alphabets. I'm going to solve for an equation in terms of that y first. So let's see whether we can use the same strategy here. I'm going to break this up into 3 to the power of 2x, 3 to the power of 1, minus this is 3 to the power of x, 3 to the power of 2, plus 6. This is equal to 0. So this, I can rewrite it as 3, and for this, I'm going to write it as 3 to the power of x to the power of 2. Minus away 3 to the power of 2, this is 9. And we have a 3 to the power of x, then plus 6 is equal to 0. So our first objective has been achieved. I managed to get an equation with just one single exponential form, and that is 3 to the power of x. So I'm going to let y represent this 3 to the power of x, which will then give me an equation 3y squared minus 9y plus 6 is equal to 0. It becomes a quadratic equation. I can simplify this definitely. I'm going to divide this throughout by 3. So y to the power 2 minus 3y plus 2, this is equal to 0. Factorizing this, we have a y minus 1, y minus 2, this is equal to 0. So y is equal to 1 or y is equal to 2, and y represents this 3 to the power of x. This is also 3 to the power of x, this is equal to 2. So 3 to the power of x is equal to 1. What does this say about x? We have discussed this. It is here. A to the power of 0 is 1. So if 3 to the power of x is 1, this tells me that x must be equal to 0. And as for this, I'm going to try to natural log on both sides. So it will be ln 3 to the power of x is equal to ln 2. X I can bring forward. So we have here as x ln 3. This is equal to ln 2. This tells me that x is simply ln 3 divided by ln 2, and we can press this into the calculator. With the help of our calculator, this is equal to 0.631. And there's one more thing that you need to know when it comes to the exponential form, and that is you drawing the graph that represents y is equal to a to the power of x. Okay, I keep saying e, like what I was telling you, you're going to be seeing this e, this Euler's number a lot, okay? But no, here we are going to just draw a more general graph. It is y is equal to a to the power of x. So please memorize the shape of this graph. This graph will have a horizontal asymptote of y is equal to 0. So the graph will tend towards the x-axis, but you will not cross the x-axis. And it has a y-intercept of 0, 1. This is obvious because at this point here, x is equal to 0. So we have a to the power of 0. And what is a to the power of 0? It is 1. So the corresponding y-coordinate here is 1. This is the graph provided that we are looking at a as a number that is strictly bigger than 1. But if a is not strictly bigger than 1, we are going to be looking at a to be between 0 to 1, which means that we are not looking at a to be 0, we are not looking at a to be a negative number. So if a is between 0 to 1 instead, then we are going to have a graph that is like this. Again, please memorize it. It has some common features as the case when a is bigger than 1, which is it also has the same horizontal asymptote y is equal to 0. So the graph will tend to the horizontal asymptote y is equal to 0, but you will not touch it. And it has a y-intercept of 0, 1. And it is the same thing. When x is equal to 0, we have a to the power of 0, and the corresponding y-coordinate is equal to 1. I guess that's all I have for the chapter on exponentials, and I'll just see you in the next topic.